Greetings, my name is Jason Andres Lara Jimenez. I am a undergraduate senior at the University of Puerto Rico, Rio Piedras campus, and today I'll be presenting my summer research project titled The Effects of Galactic Cosmic Radiation and the Neuroprotective Antioxidant CDDO-EA on the Acquisition of Stimulus Response and Extinction Learning in Female Mice. This research was done in the ICE lab at the University of Pennsylvania. First, I wanted to let you know that the Mars mission is being targeted for the late 2030s, and this is much closer than you may think of. And their research projects currently working for this are the Artemis and the Deep Space Gateway program. With the Artemis program, NASA will land the first women and next man on the moon by 2024, using innovative technologies to explore more of the lunar surface than ever before. Using what they learned of the moon, they plan to take the next giant leap, which is sending astronauts to Mars. And the Deep Space Gateway goal is to have crews fly at increasingly larger distances from Earth for increasingly longer periods of time into the interplanetary space. And the eventful crewed mission to Mars will be an approximately 3-year round trip. However, we are facing obstacles which we must address to get closer for mission success. The deep space environment consists of high energy charged particles, mostly originating from galactic cosmic rays. And unlike X and gamma radiation, charged particles deposit energy along their paths, resulting in dense cores of reactive oxygenated species. And GCRs are so energetic that they penetrate spacecraft shielding, prompting the need for alternative approaches to protection. And high levels of oxidative stress can cause cluster lesions on DNA, resulting in double-strand breaks. And this in turn leads to different biological outcomes than traditional radiation qualities. With that being said, there are major issues in the central nervous system space radiation literature. An issue with the behavioral literature is that radiation risks to the central nervous system have been informed by classical open arena-based behavioral tests, such as the elevated plasmase and the open field test, which introduces a confound in rodents who, as prey species, are endogenously anxious in open areas. And previous studies on the brain and behavior effects of GCR have been heavily biased towards males, though the astronaut population consists of both sexes. Um, Studies assessing the effects of charged particle radiation on the central nervous system to this point have relied on monoenergetic single particle studies, which is highly uncharacteristic of the broad GCR particle spectrum. And currently to this point, there is no data from human exposures due to Earth's radioprotective magnetic field, prompting the need for animal studies. For our aims, due to recent findings suggesting the female rodent brain may be less susceptible to radiation-induced cognitive deficits than the male rodent, we aim to test 6-month-old female mice for cognitive performance in a rule-based acquisition and extinction task on a touchscreen-based appetitive platform. And the naturally derived antioxidant compound CDDO-EA has been observed to be a powerful mediator of cellular redox homeostasis and subsequent pathologies during high oxidative stress inducing conditions. And due to these benefits, we aim to test CDDO-EA as a candidate radioprotective countermeasure in a subset of female mice exposed to an acute, mission-relevant 750 milligram dose of GCR. By comparing cognitive performance to naive mice receiving GCR, mice receiving only CDDO-EA, and naive sham irradiated mice. For our hypotheses, based on previous studies using various models of GCR, we expected female mice to exposed to GCR would take more time to complete the acquisition and extinction tasks than their sham irradiated counterparts. Furthermore, due to its neuroprotective properties, we predicted that mice given the antioxidant promoting compound CDDO-EA and GCR would avoid the cognitive impairments brought forth by mice exposed only to GCR in both tasks. And in addition, we predicted that the sham irradiated mice, which are given CDDO-EA, will complete both tasks faster than the group mice that received the control chow and sham irradiation. Thankfully, the iChe lab offers possible solutions to fill these literature gaps. with experimental approaches that meet all these criteria. To replicate the effects of GCR, female mice were exposed at NASA's Space Radiation Laboratory to an acute mission-relevant dose of 750 milligray of a ground-based GCR replication using 33 particles at various energies or to sham radiation. And 3 days before, during, and 1 day after radiation, mice were also given control chow or chow containing the antioxidant CDDO-EA as a potential radiation countermeasure. CDDO acts on the NRF2 KEAP1 pathway by binding and inducing conformational changes to KEAP1 molecules, preventing them from inhibiting the expression of antioxidant genes. And mouse cognition was studied using an appetitive touchscreen behavioral platform 9 months after radiation. Mice learned or acquired a simple stimulus response operand task and then learned to extinguish that task. During acquisition, mice needed to touch a white square that appeared on the screen, and correct touches were rewarded with a strawberry milkshake. And during extinction, mice learned to no longer press the white square as they no longer receive a reward. So for our results section, most of my work during the summer consisted of data analysis and validation of acquisition and extinction learning in different parameters. For the criteria to complete acquisition was receiving 80% correct rewarded responses for 5 consecutive days. Mice receiving control chow and GCR took significantly longer to complete the acquisition task when compared to every other group: control, chow, cham, CDDO-EA cham, and CDDO-EA GCR. And for the extinction, it was the criteria to complete it was 30 correct response submissions for 3 out of 4 consecutive days, and there were no main effects of diet or radiation, and no diet radiation interaction. For our conclusions, mice that were exposed to GCR took longer to learn a stimulus response task, and this GCR-induced cognitive deficit was prevented by CDDO-EA. There was no effect of GCR or CDDO-EA on extinction, and our results suggest a mission-relevant dose of GCR is harmful to the CNS, but CDDO appears to prevent learning deficits. Future work should further assess CDDO as a countermeasure to space radiation. Before I finish my presentation, I want to thank the Summer Undergraduate Internship Program for giving me the opportunity to be part of this lab, and not also that, to expose me to state-of-the-art research, and also the ICE Lab for giving me valuable tools that I know that I will use throughout my life, not just only as a scientist, but as a person. And this research could not have been done without our funding from the Children's Hospital of Philadelphia, the Translational Research Institute for Space Health, NASA, and the NeuroID program. If you have any questions, please let me know. I hope you enjoyed my presentation.